Today, I want to code the forward pass for a single layer perceptron in Python using Numpy. Okay, so right now I have open Google Colab, which is very nice if you don't already have something set up, because it has all the Python tools that you might need already built in. So you just need to sign in with your Google account, create an IPYNB file, and then that's it. It will have everything built in. Here I have the sigmoid function, the activation function that squishes all your values between 0 and 1 and introduces nonlinearity. So I have the sigmoid function, and I never actually showed what it looked like. So this is what it looks like computationally wise. It is 1 over 1 plus e to the minus x. And if you don't know what e is just a number, and we're raising it to some variable power, x, right? And it's like 2 to the 2 is 4, 2 to the 3 is 8, and so on and so forth. So e is just a number. It's roughly equal to 2.718, and the decimal goes on forever. But it is, at the end of the day, just a number. And to prove to you that this is the sigmoid function, I've graphed it on Desmos, the graphing calculator. And we can see 1 over 1 plus e to the minus x. It is the same, and it indeed has us between 0 and 1. Okay. So if we're going to be using NumPy, the first thing we're going to want to do, coding-wise, is going to be import NumPy as NP. Okay, and we're going to run this. And the nice thing about NumPy is that it has something called NumPy arrays. So if I create a NumPy array, I'm going to store it in variable ARR. A NumPy array is just like a list in Python, and this is how we create it: NumPy array, and then parentheses, and then we put in our list. And it is just a list, but it has a little bit more functionality. And NumPy also has a lot of mathematical functions that are very useful when it comes to making neural networks. Also, we can make NumPy arrays that look like matrices. So if I create matrix equals np.array, np.array, and then I can create sort of 2 rows of lists, right? Just like you would have in a matrix. Or I could even add another row if I wanted to. And 5, 6. And print matrix. And then when we print it, we will see that we have 3 rows, 2 columns. That's very nice. We can print matrix.shape. And we can see 3 rows, 2 columns. Shape is the same thing as dimensions. Yeah. So we can model matrices. We can make matrices in Python using NumPy. So that's why we will use it for coding. So the first thing I want to do is to create a template for my layers in a neural network. Neural networks, for a single layer perceptron, I could have any number of inputs for my layer, and I don't want to really hard code what the number of inputs want it to be. I want it to be very easy to change the number of inputs. And this will be even more useful when we get to having multiple layers in our neural network, because then we will just have a template and we can copy and paste the template for each layer. So a template in Python is analogous to a class. So when we create an instance of our class or an object, it will have all the same properties of the class, and then we can introduce some variable properties. So for a single layer perceptron, the layer will have a variable number of inputs, right? It could have any number of inputs. We can choose any number of inputs we want. So I'm going to use the def init function, and this is called whenever we create a new layer, whenever we create a new instance of the class, and we have to pass in self, and then whatever we want, changing number of inputs, okay? And so what does a layer have? A layer has weights and a bias, right? And the weights have dimension. In the last videos, we said they have number of inputs for the number of rows and 1 for the number of columns. So given that we have a single layer perceptron with this number of inputs, we want to create a weight matrix with this dimensions, where the number of rows is the number of inputs and one column. And I just want to create a random matrix for now. So I'm going to create self.weights. I'm going to assign the attribute weights to the self, to the layer. And I'm going to say self.weights equals np.random.randn will help us generate random arrays in Numpy. And I can put in any shape I want. And the shape I want, or the dimensions I want, is number of inputs, comma 1. Self.weights equals np.random.randn, and then this. Okay? And I'm just going to run this really quick. And if I go over here and I say SLP, single layer perceptron equals layer, I'm going to create an instance of layer, and then I can pass in number of inputs equals, let's say 3. Okay? So if I print slp.weights, if I print the weights, I expect that they will have dimensions of 3, 1. So 3 rows, 1 column. And indeed, we do get 3 rows and 1 column, and these are random values in between. Something else we can do when generating random numbers is we can set a seed. So I can say np.random.seed, we can say 1. If I don't have this seed and I create a new instance every time, you'll notice that the random numbers, they change. So I have random numbers and they're changing every time I run it. If I set a random seed, I will generate random numbers, but if I do it again, oh, I didn't run this. Okay, I need to run this, rerun it. It will generate random numbers, and if I run it again, it will generate the same random numbers. And this helps us make code that is repeatable and it's more consistent, and sometimes we just want that consistency. So I will just put that in there, np.random.seed1, and I could put seed2. It's this just going to be new random numbers. So if I run this again, now I have new random numbers, but when I run them, they are repeated over and over again. It doesn't matter what seed you choose. Okay, so now I created my weights. I also need bias, right? Don't forget. Bias dim is going to just be just a number. Just a number. What is going on? Okay. So the bias is just a number, so self.bias equals np.random.randn, and we don't need to put in a shape because it's just a number. If I run this, I can also print slp.bias, and now it's just a number. It's a random number, and we set the seed, so it's just going to be the same random number over and over again. Nice. We assigned our weights and our bias to our and also we can, if we look at it, we can change the number of inputs, and now it will actually give us a new one, but it's still repeatable. Weights, if we print the weights, now we expect to have 4 rows and 1 column, which we do. So it works. It's a template, right? We can put any number of inputs. Okay, next thing we want to do is to code the forward pass. Forward, always pass in self. And then we're going to have a input matrix X, right? So for now, we're going to say pass. And the output of the forward is going to be Y equals what? The activation of X times W, where this is matrix multiplication, plus B. So before I can code my forward pass, I do need an activation function. So I'm going to say def, we can use the sigmoid because that's the one we've been using often. Always pass in self, and it takes in some number x, right? Takes in some number x, and this is what it is. 1 over 1 plus e to the minus x. I'm going to say return 1 over, parentheses, 1 plus, and e to the minus x, there's a nice function in NumPy, np.exp. And this is e to the, and then we're going to say e to the minus x, so negative x in here. And that's our sigmoid function. So now we have what? Well, we know we're going to say z equals, in the last video we said it what? It's x, w plus b. Okay. So this is matrix multiplication. NumPy has a nice np.matmul function for matrix multiplication, and it will multiply x with what we want, w, our weight matrix, self.weights. X with self.weights. And then we want to add the bias plus self.bias, and this is z. And now self.output, if I want the output, I need to pass z through the activation function. So self.sigmoid z. And that should be it. If we do this, we have a layer with 4 inputs, and now we can print weights. These are the weights. Print the bias, SLP.bias, and now we can also print output, which is going to be the SLP.output. But before we can do that, output is only defined. Notice output is only defined when we inside forward. So we need to run forward first, SLP.forward. And then we need to have some inputs x. And we can have any input x, let's just say, not random, mp.array. And what? X has to have what dimensions? X has dim. In the last video we said it has 1 row and num inputs for column. In this case, num inputs equals 4, so we need to have it to have 4 columns, so that we can put in 1, 2, 3, 4. Okay. And that should be it. SLP.forward x, we pass in x into the forward pass, and then that will generate our output. And we see our weights. They are 4 rows, 1 column, number is a bias, and we have our output. Nice. So we generated our output with NumPy in Python. And so this is how we will code the forward pass in Python. And next time, we will get more into how we can make our model actually learn, which is when the fun starts. All right, see you next time.